presentation on clean energy and the environment. We have assembled a very distinguished panel from the academic world, chemistry, engineering, history, business, and also practical side of business. So the way we'll proceed this morning, because we're running a little late, and I've been told that irrespective of the late start, we must end at 12:30. So I'm going to be disciplined about that. I'm going to ask each of our panel members to very briefly introduce themselves, tell something about them with respect to today's topic. And after that brief introduction, each member will make a brief presentation to start the discussion going. After each member has made a short 10 to 15-minute presentation, then we'll open for discussion with the audience. So let me begin by turning it to my colleague on the right here, Dr. Joseph Pratt.
I assume you can hear us. It's a small group. My name's Joe Pratt. I'm a Gulen Professor of History and Business at the University of Houston. I've been studying the oil industry since I was born. My dad was a refinery worker in Port Neches, Texas, and I spent about 15 months in the refineries myself and pipelines working my way through college. So every time I've had a choice in a school from Rice forward as an undergraduate, I've written about oil. Assign me and give me my choice. It's always about oil, and I suddenly find myself described as one of the leading historians of oil in the world because it's about 8 of them. I'm in the top 10. I've written about the oil industry all my life, the history from 1973 forward, and that means I've written about Houston, and I teach both 500-person freshman history classes at U of H and 30-person executive EMBA classes on energy markets. So it's been a U of H. I'll put in my bid on U of H. It's the most glorious campus in the world that I've ever been to, certainly in the U.S. The diversity of our student body is amazing, and if you can't enjoy teaching at U of H, you better get another profession.
Very good. My name's Marty.
I'll do it the last. So.
Okay. Pardon me. My name's Marty McVeigh. I'm chairman of Safi Energy Limited. We are a British Virgin Island corporation. We handle the practical side of alternative energies, so focusing on biofuel. We currently have operations in Mozambique and Kenya. We're looking to expand into Benin as well, hopefully into Turkey at some point soon.
My name is Bora Karayaka. I am assistant professor with Texas A&M University at Corpus Christi. My specialty is with power systems, and specifically with clean, renewable energy supplies and research. I had a background with electrical engineering, and I graduated from Ohio State University year 2000. Worked for industry, computer industry, communications industry for about 10 years, and decided to go back to faculty, academia, and this is pretty much my first year. So trying to do research, and then I will have a presentation on clean energies. Thank you very much.
All right, I'm Jaffer Yavuz. It's pronounced Jaffer, not Kafer, and if you say Kafer, it's infidel in Turkish. So watch out. Some people prefer to call me Jeff too. I was in Houston for about 6.5 years before 2007 when I moved to Santa Barbara to do my postdoc, and right now I'm in the market for landing a faculty position, and imagine how difficult that is in this environment. But I'd like to establish my research program around clean energy environment, because right now I'm dealing with carbon dioxide research, and also I'm getting involved with natural gas research as well. So one of the difficulties is like cutting down from 25 minutes to 15 minutes, I guess, today, or 10 minutes. Should I start?
Well, since you're at the podium, we'll begin with your presentation, and then...
Oh, yes. You can sit in the front.
Yeah.
So can everybody see the screen now? Is that... when I was here at Rice, I did my PhD in nanotechnology area, And what I would like to introduce you the concept of open sourcing, which is basically we experienced that in terms of tackling some challenges, and the idea is how can we learn from that experience. And you're going to see some of what we have done here, and then I'd like you to think about in that context what we can do about the greatest challenge of humanity right now is the energy and environment. So basically the open source is the idea of taking, well, it's been developed by the software engineers, that you take a code which is developed by the developer, you go to the sort of semi-developer, semi-user, then somebody deploys it and we use it, then we feed it back. So it's sort of a community of people who are not bounded by the laws of patents and copyrights, right? So they're really free environment to go in fast pace. And you see the examples are mainly in the software business. So to introduce you a little bit about nanotechnology, this is a business slide, but what I want you to take out of here is the size diagram, which goes all the way to angstrom level, which is the atomic level. And right about here is 1 micrometer. Around this area is the human hair, the 60 micrometers. And what I was operating most was around this area, the nano world. So basically what nanotechnology is bringing us is 3 things. And one is the surface area. Imagine dissolving a sugar cube in a water versus a powdered sugar, and powdered sugar, of course, goes into water faster, right? It's the surface area which gives the contact surface a lot higher. But the other is the nanomagic, I call it, which is its colloidal properties. It holds the crystals which are bound to precipitate in normal conditions in the solution. So they remain in the solution. They hang around as if they're dissolved, but retain their solid properties. So the nano, since it's the size, is what's being really sort of emphasized, is also size-dependent properties, like what size of nanoparticle is, for example, effective in this technology or not. So this is, so just give you the technology we developed. It's very fine iron oxide nanoparticles. Some call it nanorust. They're basically a little bit of rusts that you cannot see by visual eye. So these are electron micrographs of different iron oxide nanoparticles. And you see our method which we developed at RISE is a lot superior than the others because it's very uniform, very individual, so you get the most out of the nanotechnology this way. What we have shown was that these guys can be removed by a magnet, handheld magnet, which was not sort of believed to happen because the theoreticians calculated that this is impossible to happen. So we were able to show it, and of course that got a lot of attention. But it was the most effective in a very unprecedented area, which is the arsenic problem. If you're aware of it, there are hundreds of millions of people right now in the Southeast Asia, which is Bangladesh, West Bengal, and that region, are continuously, every day, exposed to high levels of arsenic contaminants, which will kill them in the end because they develop skin cancers. At most, they will live 20 years. And there is no viable solution at the moment. And also, the public, in the public eye, arsenic is not a danger because it doesn't have the odor, it doesn't have the smell, it doesn't have the taste. So it's hard to convince those people who are really poor that there is a problem in their water until they see the effects on them. So there are a number of challenges. And the greatest challenge, however, is they're poor. They cannot afford infrastructure of water treatment. So you cannot get out of from their water the arsenic from their water because they cannot pay for the electricity for pumping and everything, which we enjoy in the West. That it's well established. We do have arsenic problems in these areas too, but it's all being cleared up by those magnificent pumps. So our particles did greatly, quite the opposite of the anticipation. Iron oxide, by the way, the rust is known that it will stick to arsenic. Our particles sort of managed to be a 1,000-fold better than anything existed. So this really was the breakthrough in the science of arsenic removal. However, of course, it got news coverage. It was the problem was it was too expensive. Imagine these particles are $2,600 per kilogram. So imagining that we use these in water treatment is unbelievable, because you can buy bottled water a lot less, right? Instead of giving those people in the poor countries these nanoparticles, you would rather give them the bottled water. So the question was, in the last 2 years of my PhD, I was trying to come up with a sort of an alternate way of making these particles which would be used in arsenic removal. So the quest began with engineering, that I wanted to make a sort of continuous reactor, something that outputs 1 gram per hour, and we succeeded with relatively smaller particles. But then I'm skipping a lot of things in between, but a lot of research we have done. But we were able to substitute the reagents, like the things that we use to make nanomagnetite, were 3 things, and one of those was surfactant, which is fatty acid, which is actually oil-based chemicals, edible oil-based chemicals, and so fatty acid mixture is what we intended to use instead of the high purity chemical, and I have seen that it's in the edible oils in large quantities. So I came up with a new plan of making nanoparticles. If you're really familiar with any laboratory work, this is as crude as it can get, right? Because you have very high purity chemicals in the laboratory. You use them in very controlled fashion. It's all pure and everything, but yet we're trying to propose a way to make them in almost at a kitchen setting with no laboratory sort of control, right? So this was our scheme. Soap would be acidified into oleic acid, rust, and whether or not we will get magnetite. So I started out with absolutely no laboratory grade stuff. I bought these from the grocery stores of Houston, and it began with the soap making. So I made soap first. It's olive oil soap, and then I grind it into a pan with vinegar, and I ended up with fatty acid mixture with vinegar, right? So then I was able to get some rust from. It wasn't hard to find. And I baked it for 2 hours. Even I didn't use any lab coat, so it was apron. And at the end, we were very fortunate that this reaction worked perfectly. So in chemical standards, this is unbelievable. Like you are using extremely crude starting agent reagents, and you're ending up with almost even better quality crystals than you would with the laboratory levels, which is quite remarkable. So, and I got my high school interns also try this. 3 students tried this separately. They did everything themselves, which also shows the way to make them is pretty well sort of easy in a good way. And also I was checking whether there are clues of the reaction progressing, right? So that's another thing. In laboratory, you know when the reaction is ended by spectroscopic methods. But if you're doing in a kitchen, in a pan, so you have to have some indicators that the reaction is progressing, the reaction is ending. So we were able to observe that smoking starts when the magnetite nanoparticles are forming, but they end when they're done. So this is really clear identification of the nanoparticles. And we were able to bring them to water phase, because imagine they're made in oil, so you have to put them into water. And we used some of the soap we began with to push them into water, and they did. So this summary of the technology was, we call it sustainable nanotechnology. Very crude ingredients, it's easily manageable, and yet you can make a filter. I can't see it, but you can see it over there. which could be used in arsenic removal. And the cost comparison